All right, so section 6.2, we're going to talk about inverse functions and relations. So learning targets, I can find the inverse of a function, and then also I can determine if two functions are inverses of one another. So what I'm going to do is I'm going to start with the relation. Let's call it A. Oops. And there's just going to be a set of some ordered pairs. We'll start with 1, 5. Then we'll also use 2, 6. And we'll use 3, 7. Bonus, if anybody can tell me what kind of function that would be, that would pass through those 3 points. Not a parabola. But it's linear. The slope or the rate of change is constant. As our x's are going up by 1, our y's are going up by 1. It's the same slope all the time, so we know it would be a line. But we're just looking at this ordered pair, and we're talking about inverses today. So I want us to find the inverse of that relation. Now, inverses, the notation we use, if I don't want to write out the word inverse of A, the notation that we use to imply inverse is to give an exponent of -1. So here I'm symbolizing that we're doing the inverse of A. If you have an ordered pair 1, 5, anybody know what the inverse of that ordered pair would be? 5, 1 is correct. The next one, 2, 6 would become 6, 2. And instead of 3, 7, I would have 7, 3. That would be the inverse of that relation. So if we're given sets of ordered pairs, that's really all you have to do is swap the x and the y's. But most of the time we're going to have a function, which is not just a set of points, but an actual equation. Okay, so I'm giving an f of x function. F of x equals 2x minus 5. And I'm saying to find the inverse of f of x, or f inverse of x. Notice how we write the inverse of f of x. The exponent of -1 goes on the f, not on the x. So what do we do here? Well, remember f of x is like a y. In the relation up above, we just swapped x's and y's. That's what we do in the equation as well. So your x and your f of x are just going to swap places. So instead of writing f of x, I would write x equals 2. And then instead of x, I would write f of x. Could write a y. And technically, because I'm doing the inverse, I'm going to make my notation on there that it's the inverse so I don't forget. So your f of x becomes x, your x becomes f of x, but I'm doing the inverse, so I have the -1 there. And then we need to solve for f inverse of x. So off to the side for your notes. Yeah. I'm going to solve for f inverse of x. So we got a couple steps here. It looks like I'm going to have to add 5 to both sides. And then I have to divide by 2. I'm going to swap my 2 sides of the equation as well, but I'll divide by 2. Write it as one big fraction is fine. So I found the inverse of the function there. I'm going to do one more of those, and then we're going to go back, and I eventually want to come back and graph both f of x and f inverse of x, so we can see how their graphs compare, but we'll come back and do that after we practice one more. Okay, so we have g of x. Let g of x equal -1/2 x plus 1. We're going to find the inverse of that. So same steps as before, except instead of using f, I used the letter g this time. So my first step was to swap the x and the g of x. Notice when I rewrote my g of x, I did put a exponent of -1 on it to indicate that it's an inverse. Now I want to solve for that g inverse of x. First step would be to subtract 1. Okay, so I subtracted 1 from both sides. Now I need to get rid of that coefficient of -1/2. What would be the way to do that? Multiply by -2. It's maybe worth writing down here, times -2. That way the -1/2 and the -2 cancel. Then you'll have to distribute that on the other side. So then I've isolated the g, inverse g of x is equal to, distribute the -2, I get -2x plus 2. That's how we would find an inverse of a function. But I want us to look at the graphs of both of those functions. Let's start with that problem since I'm already right there. Let me bring up a grid. All right, I'll use 2 different colors here. Okay, I'll do g of x first. How do I intercept a +1? A slope of -1/2. You will have some problems that ask you to graph both of the functions. I'm going to label that so I can keep it separate from the other. I'll also go a different color for the other. The other has a y-intercept of +2 and a slope of -2/1. So that one's my inverse. I will come back to this picture shortly because I want us to make an observation in terms of transformations that we've learned before, how we can describe what happened between those two. But let's come back to that one. I want to take a look at the graph of the first problem and then see if we notice any similarities or any generalizations. It may have been easier to make generalizations if they weren't both linear problems, but that's okay. All right, so -5. So there's the f of x. For the inverse, maybe it's easier to think of that not as one big fraction, but as two separate fractions. So it'd be 1/2 x plus 5/2. It's maybe an easier way to graph that one. So y-intercept of positive 2.5. It's not the nicest of numbers. We rise 1, run 2. Turns out they share this common point right there. Now, if I had to describe in terms of transformations, remember that's especially a geometry topic. But if I had to describe in terms of transformations what's happened from one to the other, does anybody notice what's true of both of those problems? Take a look at that yellow line there. If I reflected f of x, the orange line, if I reflected it across that line, we would get the green line. If we reflected across that line, what is the equation of that line right there? F of x equals x. Sometimes known as y equals x if we're talking about y instead of f of x. Let's see if the same thing's true here. So it's where slope is 1, passes through the origin. Is this one also show a reflection across that line? Absolutely it does. Because really, remember f of x and x, you've just replaced them. You switched them around. So there's the line across where you switch them, so it's just a reflection. So you should always, that yellow line should pass through the intersection point, always. And that's always the line through the origin with a slope of 1. With that knowledge, let's think about just some unrelated problem for just a moment. This is just a sketch. I'm not worried about being terribly accurate, but if I had that graph and I wanted to do its inverse, what could you tell me about what the inverse would look like? If I reflected that across that line, I know this is going back to geometry. It would look like that, wouldn't it? If I would have taken that first one was a parabola, and I did its inverse, we get what looks to be a sideways parabola. Is a sideways parabola a function? How can we determine just from a graph, a picture, whether something is a function or not? The vertical line test. If it passes the vertical line test, does this pass the vertical line test? Now you can draw a vertical line that hits it more than once. It fails the vertical line test. So that's not a function. Is that important? Well, kind of, but that's, in some ways, we'll talk about that more in coming sections. But we see that one passed failed the vertical line test. It's not a function. Is there a way, do you suppose, that we could have anticipated that before ever graphing the inverse? If we look back at the original, could we have anticipated that that was going to fail? How? We call it the horizontal line test. If a function fails the horizontal line test, then what do we know about its inverse then? Yeah, the inverse is not a function. Because we know that the inverse will fail the vertical line test. So we could have looked at the original and noticed that in the original, we can draw a horizontal line that touches the original more than once. So right away, we would know that its inverse is not a function. We'll get to talk more about that type of scenario. It shows up in this section, but especially in the coming sections, and we'll talk more about that idea that how do we handle that situation? Its inverse is a sideways parabola, but that's not a function. Does that mean there's nothing we can do with that? We'll talk about that in coming days. More so. Okay, let's now come back. I want to talk about really that second learning target. If we went back up there, the first learning target, I can find the inverse of a function. That's what we just practiced. But now the second learning target is I can determine, so if I'm given two functions, I can decide if they're inverses of one another. That's kind of the idea where we're going next. So let me give two functions. I'll scroll up here. Let f of x equal x minus 7. And g of x equal x plus 7. Determine if they're inverse functions. Meaning inverses of one another. To do this, let me get rid of that background. I don't need the graph paper anymore. Just go with, okay. To do this, I could do two different problems. I could find the inverse of f of x, and I could find the inverse of g of x, and I could see if they're each other. That is an option. But what we could also do is incorporate that composition of functions that we just learned about in the last section. If I plug one of the functions into the other, they should undo each other. So there's a test we can use for this. Doesn't have a name. You can give it your own name, I guess. If f g of x equals x, and the other order, g of f of x equals x, then they are inverse functions. Which is really what the definition of an inverse function is. An inverse function is something that inverts or undoes something else. So we're, by saying f of g of x, we're saying we're plugging x into the g and then plugging that into the f. The f should undo whatever g did, and you should get whatever you plugged in. So since we plugged in x, we should get x. So let's test it on this problem. So this composition of functions is what we talked about in 6.1. So g of x was x plus 7. So that's what I'm plugging into the f function. So the f function originally read x minus 7. But that x is really a placeholder I'm plugging into it. So I have something minus 7. So you substitute in your x plus 7. So I have x plus 7 minus 7 equals x. It worked. What I'm going to do is put a little check mark there. That worked. I verified that that was true, but I also need to check the other direction. I don't just need to see that f undoes g. I need to see that g undoes f. So now plug f of x into the g. F of x was x minus 7. So I'm going to plug x minus 7 into the g function. So I plug x minus 7 into the x spot. So it'll read x minus 7 plus 7. There's also x. Check. It worked. So I would then be able to say, yes, they're inverses. Something along those lines. Let's check. Let's try another one. If you do enough of these, you might be able to look at something and kind of get an idea if it works or not. But I especially initially wouldn't rely very heavily on that. Let's go ahead and test it. Let's plug them in and see if they invert each other. So I'll first plug the g into the f. G of x was 2x minus 4/3. So I'm going to plug that into the f function. Notice where the x is, that's where I'm going to plug it in. Right, so I plug in 2x minus 4/3 in place of the x. Looks like I get to distribute that 1/2. 1/2 times 2x, that's x. Great, good start. 1/2 times negative 4/3, that's negative 4/6, so it simplifies to 2/3. And then at the end I have plus 3/4. Does that equal x? It does not equal x. Can I answer the question about whether they're inverses, or do I need to go ahead and check the other one? I can already answer the question. I know that they are not inverses. I don't need to test g of f of x. So I would stop right now and just go ahead and state that. Not inverse functions. All right, so that should be able to get you started on this section. You may encounter a couple of questions, but some of that we're going to come back to in the next section. We're not really done with the idea of inverses, but it will lead nicely into the next section.